Hello, this is Mr. Anksman, and this is going to be your first part of the section 11.2 notes on types of reactions. So today we're going to cover this combination and synthesis reaction, and we'll also cover decomposition. These other three we'll leave to a later date. All right. Now, as I'm going through the notes, you will want to have your periodic table because you will have to look up ionic charges, and you'll also just want to copy down all this information into your notes. All right. Okay, so here's the first type. It's combination and synthesis. They're the same reaction, just two different terms for them. And you should know both. I usually just say combination reactions, but it depends on where you look. So in a combination reaction, you're going to combine reactants to get one product, and that's the key here. And this is how you're going to identify this type of reaction by the fact that it has only one product. So the basic format for this looks like this. So you start off with A and B, and they're going to combine and make this one compound of AB. All right. So we go from multiple simple reactants into one more complex single product. So all right, so we're going from, again, multiple reactants to the single product. And again, the single product, this is what differentiates this type of reaction from the other four, all right? It's the only type that has a single product, all right? So here's one example that we'll work through together, and then you'll have an opportunity to try some of these out, all right? So here's the two reactants. So we have just calcium, and we have this oxygen. Oxygen is diatomic. That's what has that subscript 2. So when we put these together into a single product, we have to make a compound. And when you make the compound, it's going to be an ionic compound. So just like in what we learned in chapter 9, we have to make sure that the ionic charges will add up to 0. So when we look up the ionic charges, we have this calcium has a positive 2 ion, oxide has a negative 2 ion. So we just need one of each to write out our product. Okay? And then the last thing you do is you balance it out. So we would have to put a 2 here to balance the oxygens, and then you have to put a 2 to balance the calciums. All right? So when you're writing out the products, you want to consider the charges first, make the charges add up to 0, and then the last thing you do is you balance it out. Now these special cases all have a separate, it's going to be extra credit, and I will have a separate short little screencast for those. Okay, so we're just going to skip over them for now. Okay, all right, now we'll do some practice. And just so I can write these out, I'm going to exit out of here. So I just switched over to a Jamboard so I could write these out, okay? So these are the two reactions that are in your notes, all right? So if you want, you can pause the video and try these out on your own because I'm going to start working through these right now, okay? All right, so we want to put Ca and bromine into one product, all right? So you have to consider the charges first. So calcium forms a positive 2 charge, and then bromide forms a negative 1 charge. So when we put the products together, we need 2 bromides for every calcium, so it's going to be CaBr2. Okay? So you always look at the charges first. I don't just necessarily carry over that 2 over. It just worked out this time. Okay? So then you balance it last. So you look at the number of each. We have 1 calcium on each side. We have 2 bromines on each side. So this one's already balanced. So we don't even have to add any coefficients there. Okay. All right, the next one. Now we have to put aluminum and oxygen into one compound. So again, you have to consider their charges. So the aluminum cation is positive 3. The oxygen or oxide anion, that's negative 2. So when we put this compound together to make the charges add up to 0, we're going to need 2 aluminums and 3 oxides. So we get positive 6 and negative 6, and those charges add up to 0. All right. So then, again, consider the charges first, and now we balance it. All right, so we have 2 oxygens here, 3 oxygens here, so we're going to need a coefficient 2 and a coefficient 3 so that we get 6 oxygens on each side. Now we have 2 times 2, we have 4 aluminums, so we just need a coefficient 4 in front of the aluminum on the reactant side. So that's that one. Okay, so here's the next 4 that were in that slideshow. So again, you should pause the video and try these out. This iron, +3, so iron can form a +2 or +3, so I'm telling you which one I want you to use when you write out the compound right here, the ionic compound. All right, so you can pause the video and try these out. I'll go through them in just a second. Okay, so again, we have to consider charges on all these, all right? So strontium likes to form a +2 ion. Phosphide makes a -3 ion. So our product is going to be Sr3P2. So that we get +6 and -6. And now to balance it, now we don't need a coefficient here, we just need some coefficients on the reactant side. So we need a 2 here and a 3 there for the strontium. All right, now iron forms +3 in this case. Sulfide makes -2, so our product is going to be Fe2S3. And now to balance this out, need a 3 here and a 2 right there. Okay, the next one, calcium and fluoride. So we put the ionic compound together. It's going to be CaF2, because calcium forms a +2 ion, fluoride makes a -1 ion, and this one happens to be balanced already, so we don't have to add any coefficients. All right, Rb and N2, and fluoride and fluorine and nitrogen, those are diatomics. That's why they have those subscript 2s. Rubidium forms a +1 ion. Nitride forms a -3, so it's going to be Rb3N to make the charges add up to 0. Then to balance this, I would fix the nitrogens first with the coefficient of 2. That gives you 2 nitrogens on each side. Now we have 6 of these are rubidiums, so let's put a coefficient 6 right there. Now that one's all balanced. Okay, and that's combination reactions. We're taking elements and we're putting them together into a compound, and then we balance it out. All right. Okay, now we'll transition back to the slideshow here for the decomposition reactions. Okay, all right, so decomposition reactions are just the opposite of combination. We're going to take a single reactant and it's going to break apart into smaller pieces, a lot of times into elements, not always though. So the basic reaction is you start with a single reactant, AB, and it's going to break into its components, A plus B. So the single reactant is how you distinguish this type of reaction from the other 4. And you will have to do that once we're done here. You'll have to be able to look at a list of reactions and figure out which type it is. Well, this is how you figure out this type. If you only see a single reactant, that's going to tell you decomposition. So it's a single reactant that breaks apart into multiple products. So a lot of times all the time you have to add energy to make this happen, to break apart your reactant. So in the case of water, if we run electricity through it, it's going to break apart into hydrogen and oxygen. Now, one important thing with decomposition reactions is you have to remember the 7 diatomics, the Brinkelhoffs. So when we break water into hydrogen and oxygen, we need to know that it's H2 and O2. So we write out our 2 products and then we balance it at the end. So we need a 2 in front of this H2 and a 2 in front of H2O to get that balanced. All right, now there's also a special type here. This isn't extra credit though, this is something that you just need to know. It's called a hydrate. So when you see this like a dot or an asterisk between some ionic compound, like in this case CuSO4 and water molecules, in this case we have 5 of them, this is a hydrate, all right? And this is actually pretty easy. A hydrate, you can kind of think of a hydrate as like a sponge. It can absorb water molecules into the spaces between these ions. So it absorbs water molecules just kind of like a sponge. So when you heat these, what happens is the water will separate and it just goes out into the air. So it makes it pretty easy to write out the balanced equation. All we have to do is take this asterisk or dot and you replace it with a plus sign. So this is showing that the water molecules are attached to the CuSO4, and then when we heat it, those water molecules become separated from the CuSO4. So you don't have to worry about charges or balancing. We just take what we have here for the hydrate and replace the asterisk or dot with a plus sign. Okay, so that's how you deal with a hydrate. All right, now for the practice, I'm going to switch over to a Jamboard again so I can write on this. Okay, so here's the first 2 examples from the slideshow. So we're just going to break apart these compounds into elements, and really, like what I said, you have to remember the diatomics. All right, so we're just going to have calcium, and we're also going to have iodine. Now iodine is one of the diatomics, so we just need the subscript 2. If it's a diatomic, we need the subscript 2. If not, we just leave it with 1. All right. So write out the elements, and then we balance it at the end. In this case, it's already balanced. All right. K2O, it's going to separate into potassium and oxygen. So potassium is just K. Oxygen, being one of the diatomics, is O2. In this case now we need to balance it a little bit. So we're going to need a coefficient 2 right here in front of K2O to balance the oxygens. That gives us 4 potassiums. So we need a coefficient 4 there. Okay. All right, now these last 3, again, pause the video and try these out. I'll go through them in just a second. Okay, so for these 3 now, again, we're going to separate these first couple into elements. So we have sodium, and we have nitrogen. So nitrogen is a diatomic, so we need the subscript 2. And now we balance this, so we would have to have a coefficient 2 to balance the nitrogens. And then that gives us 2 times 3, so now we have 6 of these sodiums, so we need a coefficient 6 right there. Okay, the next one, Mg3P2, so that's going to break apart into magnesium and phosphorus. Phosphorus is not a diatomic, so we don't want a subscript 2. So then we just have to put coefficients in front to balance it out. Okay. One common mistake I see is that when people separate the elements in this decomposition, they just carry over these subscripts. You cannot write a subscript right here. Okay. The only time you write a subscript is if you have a diatomic, like nitrogen. That's where it requires a subscript 2. Otherwise, the rest of the elements, you just write down one of them and then you fix the difference by balancing. All right. So anyway, the last one here, this is a hydrate. So we just have to rewrite the reactant with a plus sign rather than that asterisk to show that now the water molecules are separated. Okay, so this is a hydrate. Spell that out quick, sorry, it's kind of sloppy. And then when it breaks apart, when it doesn't have water anymore, now it's called anhydrous. Okay, so hydrate when you have the water molecules attached, anhydrous when the molecules are now separated. Okay, and that's all the notes for these first couple reactions. Have a great day. Bye.